All right, guys, how's everybody doing? Professor Brian back with another installment of Workout Wednesday. Today, we're going to be focused on Chapter 19, Chemical Thermodynamics. I wanted to do some more examples that were calculation-based. Didn't think we had enough videos for that. So we're going to take a look at a problem that is actually from the worksheets in the supplemental worksheet area of the particular D2L module, and it says that metallic iron is produced by a high temperature process through a series of reactions, one of which is shown below. Find the various parameters requested using the data which can be found below. So we have been given a balanced chemical equation of iron 3 oxide reacting with carbon monoxide to create iron 4 oxide and CO2. Fe3O4 and CO2. Okay, so what is the given data? In this case, they want the standard entropy change, right, which is delta S naught. Standard entropy change for the reaction, and they have given us entropy data, right? This data is either going to be given to you in the format of a table. It's going to be given to you in the format of reference materials. For you, you can find it in the back of your textbook in the thermodynamic quantities. So let's take a look at how we would approach this particular question. What I would do is I would write the chemical reaction first. Fe2O3 plus CO gas. And phasors are going to be important here because you want to make sure when you're looking up the data that you are using the data associated with the proper phase. CO2 gas. All right. So here is our particular chemical reaction. And we now have we determine that it is balanced, and we are looking at a total of 10 oxygens on both, and we're looking at a total of 1 carbon, and we're looking at a total of 6 iron. So always make sure that you are balanced, because you may not always have a reaction that is already balanced for you. They want the standard entropy change, which is delta S naught, which is equal to the sum of N moles associated with the standard enthalpy of the reactants minus the sum of standard entropy of, the products, it's standard entropy of products minus reactants. And remember, this is always the format, products minus reactants, and you can see this in your reference materials as well. We have this formula given to you in the reference materials. So now how do you apply that? Well, given the information that we have been given that the standard entropy for the products is going to be 2, which comes from here, times the value that was given in the table, which is 145.3, and that has units of joule per Kelvin mole, and this is 2 moles, of course, plus 1 times the value for CO2, which is 213.7 joules per Kelvin mole. And you need to make sure that you keep your units as 1 mole. All right. And this is minus the reactants, which is going to be 3 times the value for iron 3, 87.40 joules Kelvin to -1 mole to -1, plus 1 times the value for CO, which is 197.5 joules per Kelvin mole. Okay, so once you do this math, what you will see and what you will get is each of these values. So 2 times 145.3 is 290.6, and that's joule per Kelvin, plus 213.7, and that's still joule per Kelvin. Because we've multiplied it by moles, moles are now gone. This is all the summation, right? This is where this summation statistical sign comes from. We have summated the entropy of products, and then we're going to subtract that from the same thing for the reactants, which is going to be 3 times 87.4, which is 262.2 joule Kelvin, plus 197.5 joule Kelvin, right? So now we have all of the math complete here. Now all we do is plug this in the calculator, and our final answer is going to be 290.6 plus 213.7 minus 262.2 plus 197.5, and that should give us a positive 44.6 joules per Kelvin. Okay, so we have an increase in entropy. And if we were looking at this and we had to predict if there was an increase in entropy, we could predict that there was an increase in entropy because we are creating a more complex solid, right? More iron atoms, more oxygen atoms, and a more complex gas, right? We're going from a C and an O to 3 atoms within this. So we're creating 2 more complex, slightly more complex compounds, and we see a slight increase in entropy. So what I wanted to do, and this wasn't asked in the question, but what I wanted to also do is to try to add to this delta G. So given this particular reaction, what if I ask you for delta G? Right? What if I ask you to determine, is it spontaneous, right? Is the reaction spontaneous at, let's say, 400 degrees Celsius? What else would I need to what other data and information would I need to answer this question? Well, I would need to know the equation for delta G is equal to delta H minus T delta S, and we have delta S. We just saw for that in this first portion, and we have T because I gave that to you, but what we don't have is H. Now, when it comes to solving H, we can solve H with information and data. And what I did was I went and took the information out of the textbook, right? And this is the delta H information, the heat of formation for each of these particular compounds. And we need to do the exact same math using the exact same type of equation, because delta H is equal to summation of N heat of formation of products minus delta M heat of formation of reactants. And here I have all of that data, right? Here I have all of that data. Sorry, let me move this over. Okay. So I need to plug this data in very much similar that I plugged it in up top. So this is going to be equal to 2 moles times the value for Fe3O4, which is negative 1117.1. And now we have different units, kilojoules per mole. Got to keep that in consideration. And this is going to be plus 1 times the value for CO2, which is negative 393.5 kilojoules per mole. And this is going to be minus bracket products minus reactants. So we got 3 mole times reactant negative 822.16 kilojoules per mole plus 1 times CO negative 110.5 kilojoules per mole. All right. So now we're going to simplify this and do the math very similar to what we had done before. Okay. And once we plug this in the calculator, we end up with 2 times negative 1117.1 is negative 2234.2. So this is equal to negative 2234.2. And now we're dealing with kilojoules only, plus negative 393.5 kilojoules, because moles have canceled, minus 3 times 22.16, and that's negative 2466.48 kilojoules plus negative 110.5 kilojoules. All right, so now we have delta H is equal to these values, negative 2234.2 plus negative 393.5, and this is all minus negative 2466.48 plus negative 110.5. The answer is negative 50.72. Negative 50.72, and this is in kilojoules. Okay? Realize something. We have an exothermic, so heat is being released, and we have a entropy process that is increasing. So we're releasing heat, but we're increasing entropy. Now, if we take a look at this equation and take the information we have now, which is the temperature, the number, the entropy, and the enthalpy, we can determine that delta G is equal to negative 50.72 kilojoules minus temperature has to be in Kelvin, so we are dealing with 673 Kelvin, right? 400 plus 273 multiplied by the entropy, which needs to be in kilojoules, right? It needs to be in kilojoules per Kelvin. So this is equal to 4.46 times 10 to the negative 2 kilojoules per Kelvin. So we got 4.46 times 10 to the negative 2 kilojoules per Kelvin. And we see that we have delta G is equal to, once we plug this in, negative 50.72 minus 673 times 4.46 e to the negative 2. We see that we end up with negative 80.73 kilojoules is the delta G for our particular reaction here. And what do we know that negative delta G means, right? That this is, in fact, spontaneous at 400 Kelvin, right? And what did it say in the original question? Remember, the original question said high temperature process and a series of reactions. So we do expect that this reaction should have been spontaneous at a high temperature, right? 400 Kelvin is pretty high temperature. And we see that it is based on a negative delta G, right? Negative delta G equals a spontaneous chemical reaction. So this is step-by-step process on looking at the math associated with some of the thermodynamic calculations that we've been dealing with. And here's a shot of all of it in one shot. And if you have any questions, feel free to send me an email. All right.